Good morning. In the last class, we have briefly discussed about the MOS technology, the nMOS inverter, how it is fabricated. And today, in the beginning, I will have a discussion on how the geometry of MOS inverter affect the performance of an inverter. Okay, that's very important. So we have seen the cross-section of the MOSFET in the last class. Today we are going to see the geometry, the layout geometry. For example, as you remember, the basic MOS inverter circuit was drawn like this. Sorry. So this one is a basic MOS inverter, which consists of a driver transistor. This is what is called a driver. এই কি ব্যাপার বলো তো এইগুলো সমস্ত Thank you. You see that this is the inverter, basic inverter, where I told that this transistor is called load transistor or pull-up transistor, also called pull-up, and this is pull-down. Okay, and this particular load transistor, I told you that there may be various possibilities. The load transistor may be an enhancement mode transistor, but may be kept in either in linear region or saturation region. However, the driver transistor is always an enhancement mode MOSFET. Why? For input-output compatibility consideration. You understand why? What is meant by that? If the nMOS is enhancement mode, in that case, you know that both the drain bias and gate bias are positive bias. Enhancement mode means it is normally off. Applying a gate bias, you turn on the channel, you turn on the switch. That means you have to apply a positive bias to repel holes and attract electrons, and ultimately above a certain bias called threshold voltage at the gate, the channel gets inverted. Means there will be a lot of electrons near the surface. This electron sheath connects the source and drain, and that's how we say that the switch is on. So an enhancement mode nMOS operates with VDD and VGG, drain bias and gate bias, both of positive polarity with respect to the source. So when a switch is on and off, the output voltage also switches from a very low voltage, positive, to near 5 volt, the VDD. It may be 5 volt. So the output swing is from a very low positive voltage to a very high, means up to the power supply positive voltage. And this output is suitable for switching another such inverter which is connected to this output. You know that this is nothing but one inverter of a very big circuit. It is a building block. So therefore, in order that the inverters are compatible with each other, the high voltage, high state voltage, the one state voltage of output should be the same as the corresponding one in the input side. The zero state should be the same as the corresponding zero at the input side. It will not happen if this MOSFET is a depletion mode MOSFET. Depletion mode MOSFET is normally on. If it is N MOSFET, if it is an N depletion mode, N channel depletion mode MOSFET, it is normally on, but without any gate voltage, this is on. By applying a negative gate bias, I have to turn it off. And as a result, but what about the output swing? Is always between some very low voltage, positive to VDD, all positive. And this cannot run another inverter because here we need negative voltage at one side for turning it on and positive voltage or 0 volt for keeping it on. So off and on, you need negative and positive voltage at the input, whereas the output is providing always a positive voltage. So this is not compatible. Therefore, please remember, in an inverter, MOS inverter, that driver transistor must always be an enhancement mode device. This is very important consideration. On the other hand, the load, there may be many possibilities. It may be an enhancement mode transistor, MOSFET, either kept in saturation region or linear region, or it may be a depletion mode MOSFET also. Okay? This point I discussed in the last class. Let us now see the geometry of such inverter. Here let me define the different windows. So this one is that layout or geometry of a typical nMOS inverter. I have shown nMOS, but it is valid for PMOS also. Same thing. Typical inverter. You see that initially the fabrication, if you remember the fabrication step which I told you, normally you start with diffusion of the source drain. So this one is the drain of the load transistor, and this one is the source of the driver transistor. Source of the driver transistor, this one, and this is the drain of the driver of the load transistor. Okay, and this one is a combined source drain of the driver and load transistors. This one is a combined source drain of the driver and load transistors. All right. Entire substrate surface is covered by a very thick oxide called field oxide. I told you in the last class. Otherwise the surface is covered by a very thick oxide, which I have not shown here. But only this region shown by this violet colored rectangle here and here. The oxide is etched off, and a very thin high quality oxide called gate oxide is created. So this region and this region. So carefully study the diagram. This violet color, I don't think this color has come that well. Please remember this is blue and this one is gate oxide, the violet color. So this region, this rectangle and this rectangle shown by violet color, they represent ultra thin gate oxide. So it is clear, even if the color does not come properly, it does not matter. You see that these three rectangles are for source drain diffusions, whereas this rectangle and this rectangle, they represent a region of silicon which overlaps the diffusions. You just see that this has overlapped these two diffusions. Similarly, this has overlapped these two diffusions. They represent a region of silicon where thick oxide has been removed and a very high quality thin oxide called gate oxide has been formed. This is very important. After that, this green region here, this green rectangle here and this green rectangle here indicates the gate electrodes. The green rectangle here and the green rectangle here, they indicate gate electrodes, metal electrodes. This may be made of polysilicon in a more sophisticated technology, or aluminum or metal in the old technology. Okay, I have not differentiated between the two so far as the color is concerned. I have shown both the gate and the normal metallization by the same green color. Metal stroke polysilicon green represents metal stroke metal or polysilicon. So you see that here I have shown the gate electrode of the load transistor, and here I have shown the gate electrode of the driver transistor. This one is input. Okay? And then you also note that I have placed metal over this. Green is metal. But below that there is a red rectangle which indicates contact hole. Therefore, I have a contact hole from the drain of the load transistor here, over which I have laid a metal finger, and this is nothing but the drain of your load transistor. And this goes to VDD according to our diagram, the supply voltage. Alright? On the other hand, you come to this side, which is the source of the driver transistor. And here also you see that I have a rectangle, means a red rectangle means a contact hole. And on the substrate itself I have placed another contact hole. Have you noted that? I have two contact holes, one on the source, the other on the substrate. Then I have got a metal like this, overlapping both, and this is configured in such a way that this is nothing but the ground of my IC. The MOS IC, this is the common. Actually, in fact, form it a common ground line and a common power bus. So this is shown just one building block of the whole chip. This one is input. And similarly, you see that I have placed another contact window on the combined source drain of the driver and load transistors, and I have another metal, and this goes to the output. So this is nothing but your output. Okay? Now, if you look at carefully this particular MOSFET, you will find that the overall size of this inverter, which is a very important thing in VLSI, will depend on what? Each individual process windows. I have to do diffusion or implantation for source drain formation, and I have opened windows like this. The size of those windows are important. Then I have opened windows for the drain of gate oxidation here and here, so size of that window is important. Then I have opened windows for contact holes. Size of those contact holes are very important. And ultimately, we are metallizing the whole substrate by using a metal frame. Only before that, perhaps we have got a polysilicon here. Instead of metal, this region we prefer to have polysilicon for various reasons, which I have emphasized in the last class. But you see that all these window sizes finally determine the size of my MOSFET. And out of them, it is found these four quantities, four dimensions are very important. This is the channel length. This is the channel length of the load transistor. And this is the width of the load transistor. And combine this W by L of the load transistor is a very important parameter. Please remember this. The ratio, it is not absolutely important the absolute values of L and W of the load, rather the ratio of W and L. Similarly, in this side, you will find W by L of the drain of the driver, is another very important thing. So W by L of load and W by L of driver, these are two very important geometrical parameters involved in a MOS inverter. We shall see afterward that if we use the NELS configuration, NELS means N-channel enhancement mode load in saturation, then what do? We short circuit, we have the metallization designed in such a way that this metal and this metal, they are shorted. the gate of the load transistor is shorted with the drain of the load transistor. This is done usually to ensure that this transistor remains in saturation for the entire cycle of operation. On the other hand, if you want to keep this enhancement mode load transistor in triode region or non-saturation region or linear region, whatever you call it, there are three names for it: triode region, non-saturation region, or linear region. In that case, what do? We have to apply a separate power supply to this VGG, which I have not. This is VGG, to ensure that the channel is always on. Actually, it is not only on, it must be kept always in the linear region. There is no pinch off of the channel. Normally, in the drain side, there is a pinch off of the channel when the transistor is in saturation. Please remember this saturation, I don't confuse this saturation with the bipolar transistor saturation. They're totally different. Conceptually, they are totally different. By saturation here we mean the region where the drain current is independent of VDS. You remember that, okay? So for that, you see that this, again, for the operation of the inverter with load transistor in triode region, I have to apply a separate VGG, and one can show after that, we shall discuss gradually, that the geometry is a very important parameter in that case. I'll be discussing those related things afterward. And ultimately, it is also possible to use this to have a transistor here, which is a depletion mode device, not an enhancement mode device. I told you this is technologically more difficult, but that technological hurdle was removed, and the technology was first very commercially successfully put forward by Intel. The name which was given to this technology called HMOS. I told you in the last class, HMOS means high performance nMOS technology. Now it has come, of course, to HCMOS, high performance CMOS, the different thing, we shall discuss it afterward, okay? So it is found that we can define a ratio called beta R. Beta R which is equal to W by L of driver divided by the W by L of load. This particular parameter is found to be extremely important in determining the performance of a MOS inverter. Of all various geometrical parameters, it is this parameter, W by L of the driver, width to length ratio of the driver, divided by the W by L of the load. This particular parameter we call beta ratio is a very important, figure of merit, you can say, or a very important parameter for determining the performance of a MOS inverter. Let us see how. We shall discuss this little bit in more detail afterward. If you plot the MOS inverter input-output characteristics, this is VI and this is VO, 0 and 0. We generally expect a characteristic something like this, I'm sure. We expect, because this is basically an inverter. This voltage you can call it VOH, and this voltage you can call VOL. A standing for high state and L standing for low state, 0 and 1. In the same way, I will have my VIH here, and somewhere here I'll have my VIL, and the input output DC compatibility requires that VOH should be equal to VIH and VOL should be equal to VIL. This is called transfer characteristics. And how do you define the so-called noise margins on these characteristics? We define here and here 2 points where the slope is unity. And then this you define a voltage range here, which you can call in terms of the input or output, the noise margin in the output high state, and in terms of input, of course, this is actually called noise margin for the input low, and similarly this one can be called VI high. These two are the two noise margins of the logic gate or the inverter. VINL in terms of input voltage, it is a noise margin in the input low state, and this is the noise margin in the input high state, VINL and VINH. And in order to have a very good performing inverter, what are the requirements to be satisfied so far as this DC characteristic is concerned? First thing is this VOH minus VOL, which is called logic swing. Should be large enough. The logic swing should be large enough. This is the first requirement. And the second requirement is the two noise margins should be as high as possible. The first requirement is the logic swing should be large enough, quite large as possible. In fact, it should be approaching the value of VDD, the power supply voltage. Logic swing should be as high as the power supply voltage. If it is 5-volt operating supply, then I want ideally a 5-volt logic swing. And then the two noise margins at the low and high sides should also be as large as possible. In fact, ideally we can say it should be 50% of VDD. Half of VDD, which is very difficult to achieve. But ideally, this noise margin should individually be equal to 50%, 1.5 of VDD. And how to achieve it? That's the question. Now, if you compare the three basic inverters which I have just discussed, in the first inverter where it is n-channel inverter, both the transistors are in MOS, but the load transistor is in saturation, and both the transistors NMOS and enhancement mode. Both the transistors are enhancement mode devices, but the load is in saturation. In that case, do you know what is the VOH which is achievable? What is the VOH which is achievable for that kind of configuration? I am speaking of NELS configuration. VOH is equal to, we shall discuss this afterward, it VDD minus VT of load transistor. So in the very beginning you are in little trouble, because you see that VOH does not go to VDD, which is otherwise expected. In most of the switches, VOH is equal to VDD. But in this case, it is VDD minus VTL. VTL is a threshold voltage of the load transistor. And then, if you also want that all these things should be as high as possible, as I have just now told you, the logic switch should be very large, that means VOL should be as low as possible. Logic swing very large means VOL should be almost approaching 0 volt. And then if we want as high as possible values of the two noise margins, then what is needed? Actually, my characteristics should be like this. And then you know that at the midpoint, the slope is called transition gain. The slope at the midpoint is called transition gain. You know, if you bias, you know that an inverter is nothing but is also an amplifier. It depends on the biasing condition. If you apply an input voltage which is this much, then the inverter is an amplifier. If you apply a small AC voltage around it, it will be amplified. And we need that this transition gain should be as high as possible. Why the transition gain should be as high as possible? Otherwise, in that case, only then we can have large noise margins. If we want to achieve a large noise margin like this, so that this point is shifted here and this point is shifted here, the transition gain should be very high. And do you know what is the other requirement to be satisfied for this NELS kind of inverter to achieve that? The beta ratio, whatever I have defined earlier, beta ratio should be very high. Around more than 50. We shall discuss this point a little bit in detail after some time. So it is not only that there is a drawback of the NELS circuit, that the VDD minus VTL is, that way is VOH is little bit less, which is undesirable, which affects the logic swing. Then I need a very low voltage, low value of VOL so that the logic swing is as high as possible. And then if we also need, and that is a general requirement, that large noise margin as large as possible, then the beta ratio should be very high. And what is the bad thing of it? If the beta ratio is too high, then what is the problem? Yeah, the size of the inverter will be large and the packing density will be affected. But is there any good point of this NEL? So you see that NELS therefore is not a good inverter, I should say, because ultimately the size requirement is too large. But is there any good point in it? You don't need another supply. So one power supply, that's a convenient one. Any other thing?
You need to because we don't need another
fabrication. These are the two good features of it. Now let us see what the things now can be achieved in NELT. N-channel enhancement mode load in triode region. In that case, you have to use a separate VGG supply. This is a bad feature, minus feature. Let me put a minus sign here. This is not a good signal. But what are the other good things? VOH is equal to VDD. Good point. A positive feature. Okay? And now, another good thing about it is that to adjust the noise margins, to improve the noise margins, I can play with two parameters. One is the geometry factor beta R, and the other is called a biasing parameter, which is a function of VGG and VDD. We shall be discussing that afterwards. So two parameters come in. One is geometry parameter, and the other is a biasing parameter. The function of VGG and VDD. By adjusting the two, it is possible to achieve a relatively high noise margins. At lower values of beta. This is number 1 point, this is number 2 point, these are two parameters, and this is the number 3 point. And this is, I will again say, is a positive feature. That means if I can achieve a higher noise margin compared to any LS with a lower value of beta R, only that what I have to do, I have to have a higher value of VGG normally. I have to use still higher value of the gate supply voltage. Then you see the packing density will be improved. All right? And another thing also you can easily conceive, because in this case, the load transistor is in linear region or triode region, its resistance is less. The resistance offered by the load transistor will be less in the triode region and very high in the saturation region. Now, if it is less, then the output is connected to the input of a similar inverter. And this inverter in MOS means all capacitances. You know that. The equivalent circuit, input equivalent circuit is predominantly a capacitance. Resistance can be ignored because resistances involve the order of tens to hundreds of mega ohm, whereas capacitances may be few PFs to few tens of PF, picofarads. Capacitances are much more dominant. We don't consider resistance. So you see that inputs of all these MOS inverters are pure capacitances. So you are driving a capacitive load. This inverter is driving a capacitive load. In that case, the series resistance is very important. Lower is the value of the series resistance, quicker will be the charging of the capacitor, speedier will be the inverter. And therefore, because the load transistor here is a linear MOSFET, a MOSFET operating in the linear or non-saturation region, it offers a smaller resistance, and therefore the charging time will also be less. Therefore, from the speed point of view, NELT is superior to NELS, higher speed. Again, a positive feature. Why higher speed? I think you've understood. Because the load transistor is in non-saturation or linear region, it offers a low resistance. Therefore, the charging time of the output node is faster. It's very quick. Charging of the output node is quicker than in the case of NELS. Therefore, it gives rise to higher speed. But the worst part of it, you have to arrange for a separate power supply line, which not only affects, it is not a very advantageous thing today. And secondly, it also consumes a lot of space on the chip. Yet another power supply line has to be provided. It also, it is a wastage of space on the chip. And again, therefore, NELT is not a very. In this case, practical value, let me tell you, the beta is usually around, say, 10 to 20 is a good figure for this kind of NELT1. As compared to NELS, where beta I said that it is more than 50, typically 70 it may be. But in this case, it is 10 to 20. Only thing is you have to have a separate power supply voltage per gate, and this should be reasonably high compared to VDD. VGG is usually 2-3 times higher than VDD. Please remember this. If you now consider the other one, it is N-channel depletion mode load in saturation and triode region combined, because these configurations are such that for part cycle, for some part of the cycle, the load transistor will be remaining in the triode or non-saturation region, whereas for the other part of the voltage cycle, this will be, so it is combined NDLS/T. And this is what is known as, in the language of Intel, this is also called HMOS. Intel's language. And in this case, it is found for this particular configuration, which is very simple to realize. Let me refer back to my earlier diagram. If you now come to again the earlier diagram of the layout, how to ensure what will be the change in this schematic to realize this one, this NDLS/T, depletion mode load. Yes. I have to ensure the gate source voltage is 0, simply that. If the gate source voltage is 0, then this transistor will remain on always, because that is how a depletion mode device is defined. So what is done? Simply these two are shorted. On the layout itself, on the mask layout itself, these two are shorted. Simpler design, just like any LS. You short this and this. In this case, you short this and this. That's the only change. You don't have to provide a separate VGG and all these botherations you don't have. So this is a good thing about it. If that is so, then what are the advantages here? Let us see, what is the disadvantage? First, let me write the disadvantage. Complicated technology. So, but effectively, just a minute. Is a minus feature. Complicated technology is a minus feature. And what are the other good features? One can show that such a thing can be very successfully done with a very good noise margins with small beta r. of the order of 4 to 6. The ratio dependence is not that much there. It can be shown even beta r is equal to 1 can work, but normally you have to maintain a beta r which is 4 to 6 for this kind of configuration and achieves high noise margin for the positive, very important. Packing density wise, this is very important. Then it can be shown that it is also can achieve higher speed. And higher packing density automatically. So positive feature, and this is definitely same, these two are linked. So far as therefore the single channel inverters are concerned, in MOS, PMOS is backdated because PMOS it is slower speed, holes. It handles holes which are less mobile. Therefore, though the technology started with PMOS for historical reasons, it totally changed over to nMOS because electrons are speedier than holes. And so far as single channel MOSFET technology is concerned, single channel MOSFET technology, nMOS technology, it is this particular configuration, NDLST, is most preferable today because this technological hurdle has now been removed. All right? I think I'll stop for a few moments and we'll switch over to that.